In this video, I'm going to be introducing logic basics. Make sure that you've got your notes off to the side for this and you are filling this in as we go throughout the video. Make sure you're using the pause feature to make sure you're getting good notes down. We're going to be going through a lot of definitions today. So by the end of this lesson, what you will be able to do is first determine whether or not a claim is a statement and or whether or not a statement is a universal or existential quantifier. This will take us all of about a second. This is a definition. Then we're going to negate statements. And then given a statement, we're going to represent it in symbolic logic and use connectives to construct a compound statement. That's basically where we're going to take statements and glue them together. And we're going to glue them together with three different things. And then given a conditional statement, you're going to state its converse, negation, and contrapositive. Some of you will remember this from geometry in high school. If you don't, that's totally fine. We're starting it from scratch anyway. And then we're going to construct and fill in a truth table for a given statement. Well, yeah, more of a compound statement, but still, compound statement is a statement. So let's start by defining statement. A statement is a declarative sentence that can be objectively, meaning that it's not an opinion, okay, determined to be true or false. Not both. If something can be true and false, it's not a statement. A statement has to be able to be objectively determined to be true or false. When we say objectively, we mean in the scientific sense. That it's not up to opinion, it's not up to perception, it's not about culture, it's not about any of that. When we talk about 1 + 1 is 2, that is objective. We can measure that. It is proven to be true. So today is Tuesday. Is this statement, or is this sentence, can we determine it to be objectively true or false? Yes, this is in fact a statement. Further, it could be true or it could be false depending on what day of the week it is, but today, the day I made this video, is Wednesday, so false statement. 2 + 7 is equal to 9. So is this, first off, can I determine whether or not this statement is true or false? I can, and I can objectively measure it. If I add 2 to 7, do I get 9? Yes. Do your homework. Can I objectively measure whether or not this is true? No, this is an example of a command. This is not an actual statement. There's no way I can determine it's true or false, that you should do your homework. So to say true or false, it doesn't even make sense. I'd have to say not a statement. Truthness or falseness, okay, the parity we call a statement, it only makes sense when we're talking about statements. If it's not a statement, who cares? It doesn't matter if it's true or false. That's not even a good adjective to use for it. 5x = 20. This is actually not a statement. If I were to change, so here, if x = 4, this is absolutely true. But let's suppose x is equal to 5. Well, then I get 25 is equal to 20. Well, now it's false. So because I can make one small shift to the object I'm talking about, that's the subject of my sentence, this is definitely not going to be a statement. The Ravens are the best football team. The only way we could determine this is with opinion. And frankly, the Ravens are such not a great football team that there's not even an objective metric to say that they are the best football team. Not only is this not a statement, but it's objectively silly. If you're a Ravens fan, I'm sorry. And I'm not sorry because I may have offended you. I'm sorry because you're a Ravens fan. That's a bummer. Now, this is how we define what a statement is. Now, the way that we negate a statement, what a negation means is we're basically saying not, and the symbol that we use for this, we're going to be talking about symbolic logic, is this little swirly. We call this a tilde. And the way that a negation works is the negation of a statement is another statement centered around the same object or claim with opposite truth value. So, for example, today is Tuesday. What is the negation of today is Tuesday? Today, that's what we're talking about, is not Tuesday. If you notice, I didn't say today is Wednesday or today is Thursday. The negation of today is Tuesday, we'll call this statement T, tilde T, is this guy here. Today is not Tuesday. Okay. 2 plus 7 is 9. Okay. So for this guy, the negation of this would be 2 plus 7 is not equal to 9. If you notice, I'm not saying 2 plus 7 is 10 or anything like that. I'm still taking the same object or claim. I'm just making the opposite truth value, or I'm making a statement centered around the opposite truth value of that. Okay. So, quantifiers. So, a quantified statement is a statement that, so when we talk about a quantifier, we're talking about quantified statements. A quantified statement is a statement around something that can be measured. It can be determined through numerical value and otherwise. So it's something that is quantified. I know that doesn't sound very helpful. So there's a perfect example of universal quantifiers. So what we'll say is a quantified statement Okay, we have two types of quantified statements. There's universal quantifiers, and the way to identify a universal quantifier, there's a couple different key words there, but the basic definition of it is we include, well, let's go ahead and just start it all from scratch. This is a statement which includes or excludes every member of a set. Okay. So some key words that give away a universal quantifier. If I see words like all, for all, every, each, none, no one, etc. Ultimately, I'm talking about everybody. I'm either talking about everybody or nobody. So when I'm looking at a universal quantifier, I'm talking about every single thing included in a set. Now we've got existential quantifiers. The way we define an existential quantifier is it's a statement which shows existence particular members of a set without including the universe. Now, some keywords that give away existential quantifiers. You could say some, there exists, at least one. When I'm talking about when I have an existential quantifier, I'm talking about a particular thing or a collection of particular things within a set, but that cannot include everybody. If I include everybody, that's now a universal quantifier. So take a second and negate each of these statements. Go ahead and pause the video. You're going to negate each of these statements, and don't worry about the truth value of it because some of these statements are objectively untrue. But whatever, just go ahead and negate these. I'll give you a second, pause the video and do that. Okay, so for not A, our statement would be there are not 24 students in this class. I'm not saying that there's 25. I'm not saying there's 26. I'm not saying there's 23. I'm just saying there are not 24 students. For B, I'm negating B. Some people like history. Nobody likes history. So if I'm saying there are some people who like history, the way I would negate that is I'd say, oh, there aren't any people who like history. Okay. For C, all students have part-time jobs. So in order for me to negate every student having a part-time job, what I would have to do is show that there is at least one student with a part-time job. When I'm doing a negation, think about what your goal would be in order to disprove the statement. So if someone told me some people like history, the only way I could disprove that is by showing that nobody likes history. If you were to say, for example, some people like history, and someone were to go, no, that's not true, some people don't like history, that person hasn't negated your claim. They haven't negated your statement. The way that you negate the statement would be by showing that nobody likes history. Okay. In the same breath, if I had all students had part-time jobs, in order for me to disprove that, all I would have to do is find one student, at least one student. But if I even just find one student who has a part-time job, then we're good. I've already negated the claim. If you notice, some people like history. This is an existential quantifier. If you notice, we negated this with a universal quantifier. further. We said all students have part-time jobs. This is a universal quantifier. And we negated this with an existential quantifier. This is necessarily the case. If you're going to negate an existential quantifier, you have to use a universal quantifier. If you're going to negate a universal quantifier, you have to use an existential quantifier. If you notice, it's not common that you can ever hear politicians use universal quantifiers, whether it be in stump speeches or debates or whatever the case may be, because they're really easy to disprove, right? Now, existential quantifiers, some people, right, this is not at all hard to get away with, because in order to disprove that, you have to show that all people of a particular variety are doing that certain thing. That's really hard to do, okay? So 3 plus 5 is 8. That's going to be my statement D. What is not D? Well, that's 3 plus 5 is not equal to 8. It's certainly not true, but that's what we would have to demonstrate in order to negate that statement. Nobody likes Mondays. Oh boy. So nobody, this is a universal quantifier, so I have to use an existential quantifier. There is at least one person who likes Mondays. Gross. But again, this is a universal quantifier. The way that you disprove it is with an existential, or the way that you negate it, rather. Some cats do not like treats. That's another existential quantifier. There exist cats that do not like treats. The way that we would negate this is with a universal quantifier. All cats like treats. Okay. Now, in general, okay, and there's definitely going to be some spaces here that we get to sort of fill in. Universal contradicts / negates an existential and vice versa, meaning that a universal negates an existential, and an existential negates a universal. So some A or B, well, this right here is an existential, so I would say all A are not B. Some A are not B. All A are B. All A are B. Some A are not B. No A is B. So another way you could think of this is all A is not B. This negation would be some A is B. Okay. Sometimes rewriting a statement is going to be the most helpful thing in negating it. Okay. You can really look at this sort of template of a statement, and you could actually really think of these as kind of like rules for negation. I don't like the term rules. I like to think of them more as properties. I don't like the idea that math is about following rules. I don't think it's about following rules. I think it's more about things that naturally exist. All right. Now we're going to talk about symbolic notation. Symbolic notation is really, really great. What symbolic notation helps us to do, which we've already kind of been using a little bit of symbolic notation. If we think about each of these statements. This is not A, not B, not C, not D, not E, not F. And we even talked about our symbol tilde for negation. What I love about symbolic logic is we can take big, long, crazy statements and we can actually put them together just with symbols. So let's suppose we had a statement P and a statement Q and R. So if I had a connective, we have these different connectives. We have and, or, if, then, and then if and only if. So the way that you could write this is P and Q. We'll say P or Q. We'll say if P, then Q. And then we'll say P if and only if Q. The symbol that we use, so for and, we use this symbol. It almost looks like an A, but it's not an A. This is our or symbol. It's almost like if you were walking down the road, you choose, stop that. You choose this way or this way. Okay, it's like a fork in the road. Nothing really fancy about this. It's just quite literally just a right arrow. Okay. And then think of this as saying if and only if. That means it's a conditional statement that works both ways, hence the term biconditional. So our terminology for this, and is a conjunction, or is a disjunction. If and only if, that's what we call a conditional, and a biconditional is if and only if. Okay, so let's suppose we had our P and Q, P and Q, P and Q, and P if and only if Q. Let me draw something out about the biconditional. The way that the biconditional works is we say, if P, then Q, and if Q, then P. Biconditionals are really, really strong statements in math. They are huge. They come up super, well, they don't come up super duper often because they're really strong statements. Think about rectangles and squares. We could say all squares are rectangles, but we cannot say that all rectangles are squares. You would be hard pressed to have a statement, well, you know it's false if I were to say something is a square if and only if it's a rectangle. That's not true. There's all kinds of rectangles that aren't squares. So it's really important when you see the bicondition that you understand the strength of that statement. Biconditional statements are super strong. Now, let P represent the statement, it is raining. Q is going to represent the statement, I will go to the park. And R will represent, I will go to the movies. I want you to write each sentence in its symbolic form. I'll do the first one for you. So go to the park, that's Q. I'm saying I will not go to the park. Not is my tilde, Q. All right, take a second, pause the video, and fill out the rest of these statements. Okay, so we're saying here, I will go to the movies, or I will go to the park. All right, so then that's going to be R or Q. It is raining, and I will not go to the park. So it is raining, that's P, and I will not go to the park. In some books, you'll see that there's parentheses around that, not Q. That's fine, whatever, doesn't make a difference. It is raining, and I will go to the movies. It is raining, and I will go to the movies. If it is raining, then I will go to the movies. So that's if it is raining, then I will go to the movies. I will go to the park if and only if. So I will go to the park, that's Q. If and only if it is not raining. It is not raining. Again, hold on a second. I did something wrong. Yep, I did. God bless me. Forgot my statements. That would be a weird statement. Again, in some books, you may see parentheses there. It doesn't matter. It doesn't change the statement fundamentally. Now, here's where parentheses are important. I will go to the park. Or if it is raining, then I will go to the movies. Let's start with this statement here. If it is raining, then I will go to the movies. If it is raining, then I will go to the movies. I'll put this in parentheses because I've got if I will go to the park, okay? Or this thing. Here's where you need to be careful. If you say Q or P R, then what I could actually do here is read the statement like this. I could say, I will go to the park or it is raining. Yeah, so if I go to the park or it is raining, then I will go to the movies. That's a different statement. So the parentheses, where you put those is really important, okay? Okay, now you're gonna go backwards, okay? So now you're gonna take a statement and you're going to write it in its verbal form given its symbolic representation, right? I'll give you a second to do this on your own. Pause the video and go ahead and work this out for me. Okay, so for the first one, we have I will not play soccer. Me neither. Just bad at it. My other options here, I will, well, no, I am injured, or I will play soccer. You would do well to not try to think too much about whether or not these statements make sense. Just write them. Okay, just write them. I am injured and I will not play soccer. Okay. If I am injured, then I will not play soccer. Seems to make sense. I am not injured. And I will play soccer. Okay. I will play soccer if and only if I am not injured. Okay. If I am injured, then oof, don't go crazy. Just go ahead and write it again. Then I will not play soccer. And I will cheer for my team. Pretty good teammate, in my opinion. And H, I will play soccer. And I will cheer for my team. Okay. Now, let's go through the basic notion of a truth table. Here's the way a truth table works. So if I take a statement P and this statement P is true, its negation is going to be false, because remember, it's the opposite. So if I had a statement P and it was false, its negation is now true. Okay? Now, an AND statement. So think of an AND. So here's our symbol for an AND statement. You could also think of an AND statement as like an intersection. It's got to be in, so we'll say P, Q. If I think about these as sets, it's got to be in P and it's got to be in Q in order for it to be true. So here's the thing. Let's go through all of our possibilities. Let's suppose P is true and Q is true. Now let's suppose P is true and Q is false. Now let's suppose P is false and Q is true. And let's suppose that P is false and Q is also false. So let's think about an AND statement. If I say P and Q, and both of these things are true, think of it like, so I've got $5 and I've got, I tell you, I have $5 in my left hand and $5 in my right hand. Let's suppose I've got $5 in my left hand and I've got $5 in my right hand. Is this true? Yes. Now let's suppose I tell you I've got $5 in my left hand and I've got $5 in my right hand, but I only have $5 in my left hand. Was my statement true? No, it was false. Let's suppose I told you the same thing. I've got $5 in my left hand and my right hand, but I don't actually have it in my left hand. Well, then that's false. And suppose I actually have $5 in neither hand. Well, certainly that's false. Okay. Disjunction. This is our OR statement. It's going to look like this. Boom, boom. Okay. Now, here's the thing that's really important about OR. The way that OR works is we have what's called the inclusive OR. And what that basically means is it's going to be both or either. So either both statements have to be true or just one of them has to be true. So now let's suppose I say, all right, again, I've got $5 in my left hand or $5 in my right hand. All right. So let's consider all my options. Suppose P is true and Q is true. Suppose P is true, Q is false. P is false, Q is true. P is false, and Q is false. All right, so if I tell you I've got $5 in my left hand or my right hand, but the money is in both hands, have I lied to you? Have I told you something that's false? No, believe it or not, I haven't. Now, I probably should have just put an and there instead of an or, but I haven't lied to you. Now let's suppose I only have $5 in my left hand, but I don't have it in my right hand. Well, since I said or, this is still true. Similarly, if I've got the $5 in my right hand, but I don't have it in my left, I still haven't lied to you. I've definitely lied to you when I don't have $5 in either hand. And let me make sure that those F's don't look like E's. I don't know how that would happen, but okay. So these are truth tables that we're filling out. Now let's talk about the if-then statement. So here's a tricky one. So here's how we're going to do this one. Our symbol is the right arrow. Did I do that? Yep. So our symbol is the right arrow. We'd say if P then Q. We would write this if P then Q. This is a tricky one. So let's suppose I turn on the TV, and I've got a really old TV here. But you'll see that this is actually kind of relevant. So I turn on the news, and somebody's on the TV, and they are a presidential candidate advisor. And they say, if Kennedy is elected, then taxes will go down. Okay? So we'll call this statement P if Kennedy is elected, and we'll call this statement Q, taxes go down. All right, let's think about all the possibilities of what could happen here. So P could be true and Q could be true. P is true, Q is false. P is false, Q is true. P is false, Q is false. All right, so if Kennedy is now elected and taxes went down. Did this guy tell us the truth? Yes, he did not lie to us. That's great. Now, let's suppose Kennedy is elected, but taxes do not go down. So Kennedy is elected, but taxes don't go down. Has this person lied to us? Certainly. Yes, they have. We went ahead and elected Kennedy. We were told that taxes would go down. They didn't go down. Now, let's suppose that Kennedy was elected, or Kennedy wasn't elected, right? Somebody else was elected, but taxes went down. Has the person from the TV lied to us? Actually, they didn't. They didn't lie to us. They just said something that's inconclusive. Okay, Kennedy wasn't elected, so just because taxes went down, okay, great. But what we were saying was that Kennedy was going to lower taxes. Did the other person end up lowering taxes? Sure, but that doesn't tell us anything about Kennedy. Now, here's the little bit of a mind bender. You'd think false, false. This box here should be false. But think about this. Kennedy isn't elected. Okay? Kennedy is not elected. The other person is elected and taxes don't go down. Let's suppose taxes go up. So let's suppose the person who was running against Kennedy was Gore. I don't even know how that would work. But Gore is running against Kennedy. Gore gets elected. Taxes go up. Did the person from the TV lie to you? No. Not at all. Kennedy wasn't elected and taxes went up. If anything, that more agrees with what the person from the TV was saying. So here's where it's really important to get some vocabulary down. In a conditional statement, this is what's called the hypothesis. And this is what's called the conclusion. In a conditional statement, the only time a conditional statement is going to be false is going to be when the hypothesis is true and the conclusion is false. If the hypothesis is false and the conclusion is false, the statement was true. If the hypothesis was false and the conclusion was true, well, okay, the conclusion or the conditional is still true. It's really important that you keep that in mind. If you need to take a second and pause this video and sort of think about this, by all means, please do. I'll tell you, it really blew my mind when I first saw it. All right, now let's talk about logical equivalence. So what logical equivalents are, we have two statements. And we'll say these are compound statements. If they weren't compound, this would be kind of weird. Two compound statements are logically equivalent if they have same truth value in all cases. Okay. Now, let me give an example of this. So here's what's happening. all of these statements are just made with P and Q. So let's just start with P and Q. Suppose P is true and Q is true. Suppose P is true and Q is false. Suppose P is false and Q is true. And now suppose P is false and Q is false. All right, so let's start with P and Q. So both of these have to be true in order for the statement to be, or I'm sorry, this is an or, whoops. So if they're both true for an or statement, that's also true. True or false, well, okay, that's fine. False or true, that's still true. False or false, well, okay, that's false. All right, now, if you notice, we took that P or Q and we said not. So now the only thing I'm going to do is take everything in this column, and since I'm negating it, if it was true before, now it's false. And if it was false before, now it's true. All right, so actually, you know what I'm going to do? I'm going to make life a little bit easier for us here. Let's use our technology here for colors, because I think that'll be really helpful. So, okay, true, 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 false. And now I'm going to go ahead and negate the green column. Perfect. So then I get false, 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 true. All right, now I want to do not P. Okay, so not P. So here's P. So true, true, false, false. I'm going to do not P. So that's going to be false, false, true, true. And now I'm going to do not Q. Okay, so then that's true, false, false. So that's going to be false, true, false, true. And now I'm using the and symbol. So when both of the things in these purple columns are true, my statement is true. So then this is true, this one's false, and this one's false. Now, here's something I want you to observe. Take a look at this column and this column. No matter what's going on with P or Q, do you notice how these columns are the same? So here's what we'd say. These two statements are logically equivalent. Okay, these statements are logically equivalent. And let's actually think about this. We'll call statement A. We would say statement A, I'm going to say equals. That's not actually how we would write this in logic, but that's fine. We're going to say A equals B. Let's actually write A with words. What we're saying here is not P not P or Q is the same thing as saying not P and not Q. Goodness gracious. I'm all twisted up here. That makes sense if you think about it. Okay. Not P and not Q is the same thing as saying not, we'll say parentheses around here, P or Q. It's true. These statements are logically equivalent. Some folks get it a little twisted up and they'll say, oh, what logical equivalence basically means is that two statements are effectively saying the same thing. No, that's not entirely true. There are statements that sound very similar, and even from a solely linguistic standpoint are saying the same thing that aren't logically equivalent. Okay, so try not to get too weird about that. All right, now, converse, contrapositive, and inverse of a conditional statement. These are really important. So the way that we'll sort of make life easier for ourselves here, we'll say if you are in this class, we'll call that statement, we'll say you are in this class. We'll call that P. Then you attend John Tyler. We'll call that Q. So this is the original statement. What we've said here is if P, then Q. Symbolic logic, we'd say, boom, right arrow. Cool. Now, converse. I hear folks say conversely a lot, and they're not actually using it properly. It's like I hear folks say essentially, and what they're basically saying is basically, but that's not what essential means. Essential and basic are not interchangeable. Okay, it's the same type of thing as if you're going to say the word if you're going to say conversely, you need to make sure you're using it properly. The converse of this statement would be if Q, then P. And what would that mean linguistically? Well, we would say if you attend John Tyler, then you are in this class. Let's talk about the truth of this. Let's look at the statement. Is this statement, the original statement we have here, is this actually true or false? If you are in this class, do you necessarily attend John Tyler? Take a second and think about that. Yes, that is true. In order to be a student in this class, you've got to be a student of John Tyler. Let's consider the converse. If I attend John Tyler, am I necessarily in this class? No. There's all kinds of other classes you could be in. You don't have to be in this class. All right, cool. Inverse. Inverse, another way you can think of this is a negation. Okay. The way you would say the negation is if not P, then not Q. Okay. Okay, a negation. And we would say if not P, then not Q. How would that work linguistically? You'd say, well, if you aren't in this class, then you don't go to John Tyler. Is that true? If you aren't in this class, does that mean you don't go to John Tyler? False. That's silly. If you take someone who's not in this class, take somebody who's in, I don't know, Math 161, Pre-Calc 1. They're not in this class, but they definitely go to John Tyler. All right. Now, let's talk about the contrapositive. So contrapositive is a combination of our converse and our negation. Give me just 1 second here. So you could think of converse. It physically pains me to write this, but flip. You could think of a contrapositive as a flip and a negation. So the way this would work is it would be not Q. If not Q, then not P. Okay. How does that even work? Well, let's think about this linguistically. If you don't attend John Tyler, then you are not in this class. If you do not attend John Tyler, then you are not in this class. Well, wouldn't you believe it? This is actually going to be true. I'm going to leave the other example in the notes for you to try. But here's the big conclusion, and I'll even skip the last slide. Here's the big conclusion here. these statements here, a statement is logically equivalent to its contrapositive okay. It's the first thing I want you to notice. A statement is logically equivalent to its contrapositive. Now take a look at the statement and its contrapositive. For the statement, what would I need to have to disprove this statement? Well, I'd need to have somebody who was in this class but did not attend John Tyler. Okay, great. So they're in the class, but they do not attend John Tyler. Here, if I wanted to disprove this, I would need somebody who was not in this class. I'm sorry, I would need somebody who doesn't attend John Tyler, but is who's in this class. So if you think about it, I need the same thing to disprove statement and the contrapositive. These are logically equivalent. Next thing you need to notice is a statement's converse is logically equivalent to its inverse. For these things, I would need the same thing, again, to disprove these statements. I would need the same person. Now, the big thing I want you to walk away with here is that these guys are logically equivalent, and these guys are logically equivalent, but a statement and its converse are not logically equivalent, and the inverse and the contrapositive are not logically equivalent. So then the converse, the statement, and the converse is not logically equivalent to the contrapositive, and the inverse is not logically equivalent to the statement. Okay. Ultimately, what happens is there's two pairings of things. There's the statement and its contrapositive. Those are logically equivalent. And we've got the converse and the inverse. Those are logically equivalent. But those pairs don't interact with each other in the way of logical equivalence. My advice to you all would be to take these notes, make sure that they are all the way filled out, and then tear into the homework, slowly working your way through each piece of the vocabulary.